Hello, hello, hello. All right, we are back. Part three. Um, we are going over a series of blog posts by Jack Vanlightly. It's all about coordination, within the context of distributed systems and with an emphasis on durable execution engines, right? And I think in the last part, uh, we mostly went over um, the idea of progressible work and how um, you want reliability. If you think about, you know, your everything as a state machine and it's all graphs and the nodes of your system, or I guess you can call it the lattice or the I don't know, the matrix of all your distributed microservices. Um, so you want both reliability at the nodes and the edges. The edges being really the ways in which data flows, right? Basically, the different transitions of your state machine, um, and the nodes being, where the data lands, and you have computation, some form of computation. So you also want reliability at that point. Um, and then also I think an emphasis was put on uh, being aware of the difference between choreography and orchestration. And it's often the case that um, you want um, orchestration mostly for your critical path, right? Like it really helps bring in, shine some, I guess, bring some clarity to the overall, or at least solve the critical parts of the overall system. You should prefer using orchestration, which then fits within a bigger event-driven um, orchestra. Event-driven orchestration system. Um, yeah, I think that's a somewhat decent summary of what we've read about so far. Obviously, to some degree, oversimplifying some aspects of things, but um, you know, you can always go back and watch the last two videos, or read the articles themselves. So today we'll go over part three. There are 4 parts, so we are on track to finish all 4 parts this week. Yay! That was the goal. So yeah, we'll do part 3, and depending on when we finish, we'll see what else we want to explore after that. All right. Coordinated progress, part 3: coupling, synchrony, and complexity. So in part 2, we built a mental framework using a graph of nodes and edges to represent distributed workflows or subgraphs coordinated via choreography or orchestration. Reliability in this model means reliable progress, the result of reliable triggers and progressible work. So the reliable triggers are really, the edges, really the way in which you are, again, transitioning from one, I guess you can call it stage of the state machine of the workflows to another. So and I think it comes one of the recurring examples of the reliable triggers, are, as you will guess, mostly queues or streams, message queues and message streams. That doesn't sound right. Anyway, it's the difference between Kafka and SQS, right? And really, the simple but clear difference is that with a queue, there's really you don't get to replay messages that have been consumed already. Like it's once you've consumed the item, the message, the job, and it's been acknowledged as being done, as in reaching the final state, whether that's a success or an error, like it's consumed. I mean, you may have some log of the life cycle of the message, but there's no concept of replay. But as he mentioned, some providers might add that, the ability to replay messages from a queue, but typically that's not a typical capability of a distributed queue service. So that's why, if you want replayability, that's the bread and butter of Kafka or any other stream-oriented programming, where you push your messages and they get durably stored or persisted, in as topics or whatever. And so you can, like, consuming the messages is not actually basically, how do I put this? You're basically pulling the information, but you're not deleting the record, if that makes sense, right? Like I say, it's a different way to consume messages compared to queues. All right. In part 3, we find, in part 3, we refine this graph model in terms of different types of coupling between nodes and how edges can be synchronous or asynchronous. Let's set the scene with an example, then dissect that example with the concepts of coupling and communication styles. E-commerce example: choreography versus orchestration. Let's say we have these services. Okay, inventory, payment, shipping, notification. Okay, these are self-explanatory. So the choreography looks like this. Okay, so you place the order placed. What's funny about these things, I mean, I guess, I don't know, you get to a point where every time you see stuff like this, your spider senses tingle just a bit, and you're like, what if this order place lands, but this one doesn't? What are the implications uh, for this node here, right? Or this arrives even a second later than this one. Like, are we making the assumption that the delay will not have any effect whatsoever? In theory, it shouldn't. But then again, this is, distributed systems where you have the concept of Heisenberg's Heisenbugs, where the thing that you think shouldn't matter can end up being the sneaky little thing that's screwing things up. So yeah, whenever you see graphs like that, ask yourself, okay, well, is there an ordering or a concept of timing involved, even though these two things are meant to be independent nodes, seemingly? Like, what are the possible ramifications of these two nodes receiving messages not quite in the same order as intended, right? Because this service is dispatching these messages. We can assume at the same time to both services, but it doesn't mean that those messages will arrive at the same time. And so, does that have any implications, right? It may not, but it's still worth asking, right? Like, even though they look like they're completely independent, there may be some some sneaky dependency state-wise and timing-wise that can cause very like 1 in a million anomaly. And that's just one one section of the graph. Now you need to apply the same kind of critical thinking to every other link in the graph and understand what are the assumptions being made about the data that's being streamed or transferred via those links, given the expected behavior of the links, but also the known fault models for the links, and sometimes maybe even the unknown fault model of the link. Yeah, okay. So anyway, whenever you see a graph like that, your spider senses should start tingling, basically. Okay, so compensations are also event driven. So if the payment failed, I'm guessing, yeah, okay, make payment failed. Then you talk to the, so see, these two services do talk to each other. In this case, so there is some link here that we're not seeing in this particular view of the graph, right? I guess in this particular, I guess we can call it saga. But then in a certain mode, we do see the explicit, there's an explicit link between this service, the payment service, and the inventory service. Okay, so, and then also payment failed, so we also need to let the customer know, so we send it to the customer notification service. Okay, failure handling. If a payment fails, the payment service publishes payment failed. The inventory service listens for this and releases the reserve stock. You know what's another thing? These are things you need to consider. Well, what if it actually received this? Like, is it conceivable and possible that it actually received this for a payment that the inventory service is actively trying to load and process? As in, for whatever reason, between the time it took the inventory service to load the proper data to process the initial order placed request and the system realizing that payment failed, is it not conceivable that the inventory service is still trying to process that original request? Right. And you could make the case that, well, actually the way the system is built, that's not possible. Well, are we just saying that? Or what guarantees do we have that that's absolutely true, that there will never be a payment failed? Like, the inventory service will never receive a payment failed message while it has yet to finalize the processing of the corresponding payments initial order placed event, right? Because there is a happens after relationship here that is being implied, but the question is that actually a guarantee, an invariant of the state machine that the inventory service cannot receive a payment fail for a payment that it hasn't yet finished processing in the first place? So that would be something that you should ask yourself. Whether it's worth actually digging into is a different question, but those, that's something to think about. Little details like that. The shipping service ignores the order since it never sees both required events. I think this may be related to what I just mentioned. This is the stock. Again, that's assuming that it already has reserved the stock. Now, for fault tolerance, assuming that the inventory service is well architected or well implemented, there will be a mechanism to notice that, oh wait, I'm actively processing, I'm actively trying to reserve a stock for a payment that has already been flagged that's failed. So it needs to have a way to just bail early if you receive such a message, right? Or if it hasn't even started the process of reserving the stock, because the queue depth is pretty is pretty high, and so it's really busy processing stuff, and it didn't get to it in time. Because it's conceivable that again, those two messages land in different queues or different ring buffers of the service, right? And so maybe you have a special ring for non-failure messages versus failure messages. And so whenever it's about to pull a message from the non-failure ring, it actually somehow checks whether this is a no op, as in I shouldn't bother processing this because there was already a corresponding error message for that item. Or it may be that you also write things in such a way that it doesn't matter. Like it always processes it always processes the error messages first, as in it makes note of it so that when it's processing the non-error things, it has some sort of recall or memory that tells it, actually this element no longer needs to be processed because there was a corresponding error that came in. Anyway, there are many ways that you can handle this. I think the point being that in a purely what's the word? Event in a purely in a choreography where it's all even being passed from one service to another, you really have to watch out for assumptions that you're making as you're processing the events. Okay, so the shipping service ignores. Where's the shipping service again? Yeah, okay. So the shipping service actually never receives this because in theory it only gets triggered when it receives both a stock reserved and a corresponding payment processed. So yep, he never received both required events. Okay, key traits in action. Decouple. The payment servant doesn't know or care about inventory service. Temporal decoupling. If shipping service is down, events await in the queue. Reliable progress. Durable events act as reliable triggers of work. Emergent workflow. Easy to add new services like fraud detection that react to existing events. Excuse me. A central order orchestrator manages the entire flow. Okay, that looks like Python. Step 1, so you reserve the stock. Step 2, you charge the card. And then you schedule the delivery. And then you send a notification. And if anything fails, well, specifically if the payment fails, then you release the stock again. But then here you assume that this is gonna work, by the way. If you ever written this, code that crosses boundary or that talks to multiple microservices like that, where you're expecting things to happen in lockstep, right? You always end up in these cases where it's like, well, okay, this failed, and now I have to do something like some compensation. But then here, even in this code right here, we are assuming that the compensation steps themselves are not gonna fail, which is obviously not always the case. It may fail. Alright, key threats in action. Centralized control, easy to see the entire workflow in one place, clear conversation. If payment failed, the orchestration explicitly releases stock. Reliable progress, DEE, that stands for durable execution engine, ensures the workflow resumes exactly where it left off after crashes. Tight coupling. The orchestrator must know about all participating services. I think that's fine. I mean, if you're going with, having an orchestrator in the first place. The contrast, adding a new direct requirement for a check. Choreography, add the fraud service that listens to order placed, publishes fraud check pass failed. Update payment service to wait for fraud clearance. No changes to other services. Orchestration. Modify the central orchestrator code to add the fraud check step. Deploy the new version. Yeah, that's the tricky part with the orchestrator setup. The versioning. Right, because the durability aspect that comes from the progressible work, model means that whenever you update the code, you basically have to contend with, the concept of versioning, and you have to watch out for, like you can't just deploy the new code and call it a day, because it's possible that there are still ongoing workflow invocations that obviously started with the old version, and for some reason was suspended, interrupted, whatever, and they need to resume work. And that resumption, in many cases, makes assumption about the fact that it's still the older version is what makes the most sense to move forward with, and the new version is not backwards compatible with the work that has already been done. That's a very real problem that you have to deal with these orchestrators. Yeah, versioning is one serious challenge for orchestration-based workflows. Yeah. Adding indirect dependencies. The fraud check is probably connected to a direct edge. It is necessary for the order process to complete. Now let's add some tangential actions, such as updating a CRM, a reporting service, and logging the order in an auditing service. Each gets added one at a time over a period of weeks. This auxiliary stuff or tangential stuff is nicer from a choreography model standpoint. For the orchestrator standpoint, it's rough, and I think that's why in part 2 of this series, the article before this, there is the suggestion that going all in on orchestration is probably not a good idea overall, or going all in on choreography is also probably not a good idea. You want a good hybrid of both, where you often want the orchestration to be on the critical path, right? And that will exclude things like updating a CRM. That shouldn't be on the critical path of the order placement workflow. Let's see. Okay, so for choreography, no changes to existing services. Yes. Make the CRM reporting service and ordering service listen to the order placed and order canceled event. Yep. For the orchestration, modify the central orchestrator code to add the call to the CRM and deploy, followed by a financial reporting service and then the auditing service. Debugging a failed order. Now, yeah. From a debugging standpoint, choreography is a freaking nightmare. Yeah. Check logs across multiple services, call it by order ID, reconcile the event flow. Oof. Good luck. This is more straightforward. Look at the orchestrator's execution history. As you can see from this limited example, there are wealth of pros and cons to consider. Now let's use this example along with additional concepts around coupling and communication styles to refine our mental framework further. Refining the model further. Coupling types. Coupling is a key consideration when designing service-to-service communication. It comes in different forms, most notably design time coupling and runtime coupling. Design time coupling refers to how much one. So just to quickly map this to what we've been talking before. So design time coupling will be the orchestrator model. The runtime coupling will be the choreography model. Wait, do I have that backwards? No, I think I have it right. But I can also see how you could invert it. Yeah, that's interesting. I guess design time, maybe the better word would have been compile time. Well, actually, no, compile time is also not quite appropriate. I guess design time is appropriate. Design / implementation time, because design time or implementation time, like you can look at the code of the orchestrator and know for a fact that these two services need to exchange data between them. While for the choreography, it's just messages being sent. I mean, yes, you can semantically deduce from looking at the messages being dispatched that there is some coupling, but then again, it's not immediately obvious that like you theoretically you couldn't assert exactly which services or all the services that are in fact going to be triggered by the message being dispatched by the producing service. So in that sense, the coupling is only obvious at runtime when you're actually observing the workflow running at one time. Okay, so design time coupling refers to how much one service, a node in our graph, must know about another in order to interact. Yeah, so RPC introduces strong design time coupling. The column must know the caller's interface, expected request structure, response shape, and often its semantic behaviors, such as throttling and latency profile. Even changes to the internal implementation of the callee can break the caller if not carefully abstracted. Code that triggers work via RPC must be changed every time a work dependency changes is added or removed. Events also introduce design time coupling. Coupling, primarily around shared schemas. Yep, so when I mention semantically, just by looking at the messages. But again, like I haven't even read the sentence yet, but however, meaning it's not so obvious or direct. It's less explicit. Let's just put it that way. However, they also reduce coupling in other forms. For example, in a choreographed architecture, producers don't need to know who consumes the event or how it's processed. Yeah. This allows new consumers to be added later without changes to the producer. Services evolve more independently as long as schema evolution practices are respected. For example, the service emitting the payment processed event doesn't need to know whether shipping analytics or notification systems will consume it, or even whether those systems exist yet. This contrasts with orchestration, which may have to know about these services and have to be updated when new dependencies are added. Runtime coupling. Runtime coupling is about whether services need to be up and available at the same time. RPC is tightly runtime coupled. If service A calls service B synchronously, B must be up, fast, and reliable. Chains of RPC calls can create fragile failures or fragile failure modes, where one slow or unavailable service can stall or crash an entire request path. As Leslie Lamport famously said, a distributed system is one in which the failure of a computer you didn't know existed can render your own computer unusable. Speaking of, that gets quoted a lot, by the way, and that's because it's a very neat way to put it. I think there was something of his that came out recently that I've been telling myself that I'll get around to reading. Oh yes, concurrent program. Yeah, I know who Leslie Lamport is. I'm asking about the actual book because I know it's a work in process. The last time I read anything about it. It may not be reproducing for another person without a prior permission. Is that the same? Yeah, it's the same. Okay. The first person to report an error will be thanked in a book. Does that mean that if we don't see a thank you here, that means nobody has found or reported something? Yeah. I mean, it's pretty recent too, relatively speaking. Oh my gosh, 300 pages. What do you expect? It's Leslie Lamport. And it's called Science of Concurrent Programs. Oof. But there's so much knowledge in here. Or at least, I mean, maybe. And by that, I'm not saying that he's expounding on stuff that we didn't know before, but it's just the um, probably the very rigorous treatment that it's fine. I'll bring it later. Sorry, I was talking to somebody. Yeah. So much. So much. There's not enough time. That's the struggle, isn't it? The Paxos algorithm. Oh yeah, he's also, I mean, unless you didn't know, he's the one who came up with the Paxos algorithm. And if my memory serves me right, the initial research paper that he published on it was so, well, people just didn't really grok what he was getting at, or that he was actually exposing a distributed system algorithm, because he used some sort of storytelling device of using the English Parliament, I think. And I don't know, people just found it to be a little too thick to to grok it. And I think there were follow-up papers, not by him, by others who were basically clarifying all the things, and people were like, "Oh, okay, we get it now." Right? Parliament. No. Yeah, this was the original paper. The Porter Parliament. Yeah, so as you can already see from the beginning, he starts with early in the millennium, the Aegean island of Paxos was a thriving mercantile center. Anyway, so yeah, apparently people read through it and they were like, okay, what are you trying to say? Yeah, that's true, sorry. Yeah. Yeah, he says, I decided to cast the algorithm in terms of a parliament on an ancient Greek island. I gave the Greek legislators the names of computer scientists working in the field, translated it with Giba's help into a bogus Greek dialect. Writing about a lost civilization allowed me to eliminate uninteresting details and indicate generalizations by saying that some details of the Parliament protocol had been lost. To carry the image further, I gave a few lectures in the persona of an Indiana Jones style archaeologist. He played with Stetson hat and hip. Oh, okay. And then he wrote, I guess it was him who wrote it. Never mind, sorry. It was himself who wrote a simpler version. But although I don't know if he did that, because in between the first one or after the first one, people were like, why don't you just come out and say what you're trying to say? And he was like, okay, fine. I guess I'll give you mortals a simpler version. So a simpler version without the Greek narrative. Since then, this algorithm has become very popular and used by that was basically the sentiment I just communicated, which is okay. So I got tired of everyone saying how difficult it was to understand the Paxos algorithm, published in 122. Although people got so hung up on the Greek names that they found the paper hard to understand. The algorithm itself is very simple. The current version is 13 pages long and contains no formula more complicated than N1 greater than N2. This feels like Michael Jordan. In the NBA Finals, if he was on some college team, I don't know, maybe that's not a good example. I should stick to the sports that I'm familiar with, soccer. Anyway, you get the point, right? Like, it's like, yeah, okay, maybe to you it was entirely clear and simple, but, basically, dumb it down for us, Get off your high ivory tower and treat us like the mere mortals that we are. Yeah. And I think my understanding is that even though Raft has captured the... I don't know if this is strictly correct to say it that way, but captured the mind share or the popularity context of distributed systems protocols. I think, and I could be wrong, this is mostly based on my experience reading a bunch of things. My understanding is that Paxos tends to scale better than Raft at large scale. Yeah. So all of that is to say that, Leslie Lamport is he's cracked, as the people like to say these days. Okay, so let's get back here. He must have been thinking about RPC call chains, but request response implemented over queues can suffer some similar one-time coupling. If the timing expectation is the same as RPC, we'll get into timing expectations. It comes back to this graph here when I was telling you guys to watch out whenever you see this kind of stuff. You gotta start, your spider sense about distributed systems and clocks and time. How can that affect things, right? Like, what expectations are we What are the expectations or assumptions we're making about the order in which things happen, whether it's local or, within a certain topology of components? Um, yeah, we'll get into timing expectations in the next section. In contrast, publish subscribe using events is free from runtime coupling between services. A service can emit an event and move on, trusting that any consumers, if they exist, will eventually process it when ready. Both RPC and events come with coupling trade-offs. Okay. Events reduce direct entanglement between services, especially at runtime, while still requiring careful attention to schema contracts. Yes. RPC is simpler in some use cases, but creates tighter coupling that can make systems more brittle over time. Sync versus async, a communication continuum. My colleague Gunnar Morling wrote a nice piece, Synchrony Budget, that is relevant here. It's not too long. Who knows? Maybe we'll read this right after finishing what we're currently reading. Sorry, sometimes it's nice to just quickly glance at some of the Hawker News comments, how spicy some of the takes are. Anyway, communication between services isn't just synchronous versus asynchronous. It exists on a continuum of timing, response, expectation. I would differentiate here between a response and a confirmation. Okay. Yes, this becomes very important, especially when, you're going with this model of progressible work. Like you need a mechanism by which, you need to be able to, the system as a whole need to be able to know/figure out if a piece of work, a task, a job, whatever you want to call it, a message has been acknowledged as having reached a quote-unquote final/terminal state, which will be the confirmation part of things. Okay, so I use the term confirmation for an immediate reply of I've got this, trust me, to get it done. A service that carries out the work asynchronously will still respond with a 200 to confirm that the caller that I received the request successfully. Yes. Kafka will send a producer acknowledgement once the batch has been committed. Okay. I use the term response for a reply that may come later and possibly even through a different communication medium that contains data associated with the requested work now done. Yep, this is the this fits into the whole IO URIN type of async sender receiver model of, you have a submission queue and you have the submission and completion queue, right? You submitted something, you get an acknowledgement that your submission was received, which is not the same thing as, that whatever you submitted and the associated or the intended piece of work associated with it is completed, right? Those are two separate things, which is what is being brought up here. Like I think SSDs or NVMe IO has a thing where you submitted the data to the submission queue, and even when you do that, you still have to ring the bell, basically, to let the kernel know that there is work to be done. So in fact, what you can do is, instead of just submitting one piece of work, you can actually just keep submitting into the queue until you reach a certain level where you decide to ring the bell to basically call the kernel and be like, okay, I have a bunch of work for you to do, right? And from a performance standpoint, that's probably what you want to do. You don't want to submit one item, ring the bell, one item, ring the bell, right? You want to submit a batch of messages and then ring the bell and then let the kernel process all of them, and then give you notification when the work is completed. Okay, so I use the term response for a reply. Okay, we read that. Responses sit on a continuum. All right, need a response now, synchronous or PC. That's what we are. That's the baseline, right? That's what we are more familiar with, especially when you think about, front-end web application talking to a back-end application. Usually you're making some sort of, GraphQL or RESTful API call to the backend, and you're expecting data to just come back. Okay, yeah. I need a response, but sometime in the future. Synchronous RPC, or reliable RPC, request response over queues. Okay. And then there is no response needed, just letting you know something happened. That's more of this one is more of a broadcast. A notification. It's like you just fire and forget, basically. At one end is immediate response, where the caller needs an answer now to proceed. At the other end is no response at all, where the sender simply informs the system of something that happened. In between lies relaxed response timing, where the result is needed eventually but not right away. RPC is typically on the left. It's used when the caller needs to block and wait for the response, or the result, with a short latency requirement. Okay. One example is reserve inventory before payment in a synchronous checkout flow. This tight timing requirement makes the caller innately dependent on the caller's availability and latency, making an RPC a valid choice. Events sit on the right. They are used when a service simply emits a fact order placed without expecting a reply. Consumers handle the event independently and asynchronously. Relaxed timing responses live in the middle. Some use asynchronous RPC, like invoking a function and getting a call back later via a webhook or polling. And some use queue-based patterns. Asynchronous RPC is still runtime coupled, whereas queues act as the fault-tolerant middleware that will eventually deliver the request to the destination. While RPC and events are often presented as opposites, real systems use hybrids. RPC can be made asynchronous. Events can be used for request response with correlation IDs, but starting with a continuum helps frame the key trade-offs. Yeah. Reliable RPC previously has been delivered by fault-tolerant middleware, such as durable execution engine. This gives RPC some queue-like properties. For one, it reduces runtime coupling between the sender and receiver. If the receiver is down when the sender sends it, no worries, the RPC will eventually get delivered to the receiver, just like an event command on a queue. Using the graph terminology from parts 1 and 2, it has turned an ephemeral edge into a reliable one. In fact, I tend to think of reliable RPC as another implementation of point-to-point queues, which are either one-way or request response. Of course, this is most useful in relaxed timing scenarios. But what about resumability? If a reliable RPC is like a synchronous, okay, it's not getting any better. Synchronous RPC, but with reliable delivery. Then what about the sender's context and resuming once the result has been received? The sender is keeping a bunch of variables and context in its stack memory. And if the host fails, then it cannot resume the reliable RPC. It cannot resume once the reliable RPC has completed. Let's take an example of two-step process. Make a call to resolve a stock. Make a call to the payment service. From the same service. Oh, okay. Let's follow up. This is a relaxed timing scenario. The user has been told the order is in progress. Let's say that the first call is made. The stock gets reserved, but the calling context dies before the response is received. How does this get resumed? Let's think about this. The first call is made, the stock gets reserved, but the calling context dies before the response is received. The only way that you'll be able to resume is if somehow there is a notion of the callee has somehow persisted. There's evidence of the fact that the work was in fact, the reservation was in fact completed. So either you can this is actually multifaceted. So you need to have a way from the caller to keep track of whether it's via the edge, the reliable trigger that triggered the caller in the first place, or another mechanism like a wall or a log um, a durable log, um, where the caller somehow has a way of knowing, hey, I dispatched this response at some point, but I never got a response back. And so when it comes back, when it wakes up, it can look at its log, right? And decide, okay, this is where I was making progress and then nothing. And so that means I need to basically retry. Or another way to look at it is that it can be both, but or implies one or the other or both. So the other thing that you can do on the callee side is that when it has in fact completed the reservation, that it persists some message related to the fact that that happened, so that in this scenario, when the caller wakes up, the microservice, that's the caller, wakes up, there is a location where it can double check to see, hey, is there any work that has been completed from the callee's perspective that I never got a response for? And if that's the case, then I need to catch up, basically. Yeah. Okay, so asynchronous RPC and request response over queues address this reasonability in the above scenario in the following ways. The response is not directly received by the calling context, but via an event handler receiving a response from a queue or a webhook RPC. Yep. This is more related to the second option that I went through. So it doesn't matter that the original context is dead. It could be completely different. It could be a completely different instance of the application that receives the response. The state necessary to move on to step 2 is either contained in the response or a correlation ID is used in the request and the response. And the necessary state was written to the data store using a correlation ID as the key, so the receiver can retrieve the necessary state. The response handler then calls the payment service. Yeah, so you have the business logic, sends it to the queue, reply queue, reply queue, all queues, RPC. This one goes with the webhook. Yeah. The downside of this approach is the code is spread across response handlers, making it more complex to write, read, and debug. Reliable RPC and reasonability. With queues or webhook, the response arrives out of band, and correlation IDs must be managed manually. Some DEEs eliminate this complexity by letting you write code as if it were synchronous. The framework persists intermediate state and re-triggers the function for it to make progress. The DEE acts as the reliable delivery middleware for request and response like a queue, but also abstracts away all the response handler stuff. Yep. This is where they say it. They make it look like you don't need any additional quote-unquote defensive coding. All the code exists in one function, and if function fails, the DE invokes it again, but crucially, the code is written using the DE's SDK, and the SDK silently retrieves the state, regarding the function progress, including prior responses, so that the code essentially resumes from where it left off by using persistent state to skip prior work. Determinism is required for the strategy to work. For example, if the function starts by generating a random UUID as the identifier for the work, then a second invocation would generate a different one. Yep, so you need a way to basically, again, I think this goes back to even Article 1 when I was mentioning the fact that you basically need a way to wrap all most at least sources of non-determinism, and that usually means IO. But now you need to decide what constitutes IO, right? This is a problem if half the steps have been carried out already using a different UID. To cover those needs, the SDK will provide a deterministic UID. Basically, it will restore the result of the first UID generation or datetime or integer. Reliable RPC coupled with resumability simplifies the code. All the code can exist in one function, but can resume from a different application instance after failure. With a reductionist mindset, we could say that reliable RPC plus resumability is a convenient solution to avoid needing to build complex asynchronous response handling. But this is not a trivial aspect at all. It can make the developer's life easier and make for more readable code. Coming back to direct versus indirect edges. Bringing this back to graph model, not all edges are created equal. Direct edges represent dependencies where the workflow cannot proceed without some kind of responses. Basically the critical path. In the e-commerce flow, the order cannot be completed without reserving, inventorying, and processing the payment first. These are blocking dependencies, though the timing requirements could be short or long, or short or long. When a workflow has blocking dependencies, the coupling between the steps already exists at the business logic level. The question becomes whether to make this coupling explicit through orchestration or implicit through event choreography. The coupling cost of orchestration may be worth paying because these services already have a runtime dependency. They need each other to function. Making this explicit through orchestration may reduce overall system complexity compared to managing the same coordination through distributed event flows. So all of that is to say, pay attention to the critical path. And for the stuff that's on a critical path and has tight coupling, even at the business logic level, you should strive to make that obvious and explicit. That coupling should be also explicit, at least within this context of coordination across different microservices and having progressible work. Okay, so however, even for a core workflow of direct edges, the decoupled nature of choreography might win out. It may simply not make sense for one piece of wider workflow to be modeled as the orchestrated workflow with different technologies, support issues, versioning strategies, and deployment procedures. Also, team autonomy and team boundaries may cross such that a workflow Let's start over. Also, team autonomy and team boundaries may cross such a workflow. Wait. Why am I having trouble finishing this sentence? Also, team autonomy and team boundaries may cross such a workflow such that something is off here. And team boundaries may cross such a workflow such that, I think I get it, but it's just a little bit of a mouthful. A workflow such that the decoupling of choreography is still best. It depends. But yeah, which is basically what he's saying, right? It depends. And direct edges represent actions that are operationally or even strategically important but don't block the immediate workflow from completing successfully. The reliable and direct edge ensures that important work eventually gets carried out. In our e-commerce example, CRM updates, financial reporting, and audit logging might be business critical or legally required, especially the audit logging part. But a customer's order can be fulfilled even if these systems are temporarily unavailable. Indirect edges will also often cross more granular organizational boundaries where the cost of inter-team coordination is higher. The order processing logic is likely focused on a small number of teams in a software development org, whereas financial and auditing services like software systems are likely managed by different set of teams, potentially under different management hierarchies. For indirect edges, events match this natural business decoupling because separate concerns are decoupled. Fair enough. If CRM updates, financial reporting, and audit logging are separate business concerns, they shouldn't be embedded in order processing logic. Every time a new system needs to know about orders, the core orchestrator will need modification, deployment, and versioning. Yeah, again, going back to the versioning conundrum, right? That's the one. That's arguably the biggest thing to be wary of when you're dealing with the orchestrator method of dealing with all this. Okay, reduces coordination overhead. Teams owning peripheral systems can independently subscribe to order events without requiring changes from the order processing team. Prevents scope creep. The core workflow stays focused on its essential purpose rather than accumulating tangential responsibility. Fair enough. One thing to note though is that you can build, especially when you consider the DEEs, the durable execution engines, being a middleware, right, for your orchestrator. You could, and I mean, I don't know if this feature is supported by some of them, but you can actually delegate the part about, finding out or sending meeting messages so that whoever is interested in listening can listen. You can delegate that too as part of the middleware. Engine. Okay, so the principle is that orchestration should be limited to direct edge graphs. Okay. The minimal set of services that must coordinate to complete the core business function. Everything else should use choreography to preserve the business level decoupling that already exists. Yep. Fair enough. Alright, so in part 4, we'll finish the series with some last reflections and a loose decision framework. Alright. We made it. Part 3. So that was solid, obviously. Yeah, I mean, I think we covered everything there is to say. Again, choreography versus orchestration. Be mindful of the fact that, a hybrid is probably what you want. Be aware of the implications in terms of how, whether you're coupling things at design time or runtime. Be aware of the actual explicit business coupling and making that obvious in a code base. But also be aware of the stuff that shouldn't be on a critical path, as you're writing your orchestrator, and, find a way to, whenever you can, remove things from the critical path and instead put them at the outer edge, so to speak. You want to dispatch those as events following the choreography model, where any system that's interested can be listening to those events. Again, one thing you want to watch out for with the orchestrators is you don't want to end up with a God orchestrator function that basically does everything. You want to watch out for what does versioning means, like how disruptive it can be, especially for ongoing work that needs to be able to resume work while still having the context of the old version. And so you want to think about backwards compatibility as you're making updates. What else? To summarize, be wary of assumptions being made in terms of timings when you're dealing with the choreography of events. Be wary of the assumptions that are being made about the causality of things. That happens before. That happens before concerns. And I think that was a pretty good set of services to pick to illustrate the challenges that's involved. And yeah, I guess we'll get to part 4 tomorrow. So we are on track to do what we said we will do, which is, go through all the lectures this week. Yeah. My eye landed on these 2 other articles. Obviously we're not going to read them right now or today, but should be interesting. that's a long one. Oh my. It just keeps going. Subsequent, there were more. Were there actually more? Or this one came out in February 5. Is this the log replication? No, okay, so so there's introduction. So I guess this will be the follow-up, and then this one. Yeah, I think. Yeah, it's kind of hard to tell. No, I think this is another series of its own with these 3 articles here. In fact, it's the one before the last one. To be atomic or non-atomic, that is the question. Frisbee, I've heard about Frisbee. Oh my, this is long too. Sorry if the fast scrolling is unsettling. Refactored version. Yes, face it. Okay. Okay, so this is the original article. Okay. When an action is non-atomic execution, an action could yield at any moment to a different action in a different instance. Okay, I think it wouldn't make sense to first read the, if I were to read this, which may not be on stream. It makes sense to read this one first. Yeah, probably. Uh-oh. No. Another protocol. There's the, no, yeah, browser. If I ask you to build a table and give you a Home Depot, you will probably have a harder time than if I gave you a saw, a hammer, and some nails. I doubt that. First and all is because Home Depot stocks lumber. Oh Lord. Oh no. I'm gonna say it, but I'm just gonna nod. more so that it's not that it shouldn't exist, just that it feels like it's a hammer and it's causing people to think everything is a nail. Then it's hammering. And also, this is true, and you have to do this through ontology, uh, through ontology building and learning, leveraging everything we've learned about query engines and query engines, knowledge graphs, and ontology building. But that doesn't sound very sexy or fun. Ontology building is, it's basically like keeping your writing and keeping your documentation up to date as you're making code changes, more or less. But then you think about the fact, a place like Palantir, who are all about ontology, you do wonder how, considering that they've already taken the route of the mantra of business as code through ontology, you do wonder how much has that helped in terms of the advent of AI agents and all that. Yeah. So there's a competitive about her and the other thing. Okay. The website owner is already responsible for the human interface across many devices, and also the search engine interface. Having a standard we can use to create. Yeah, it's called the semantic web. Having a standard we can use to create what the AI sees and how to enter. Yeah, it's called the semantic web, people. When you ontologize things. Better get ready to quit your day job and get funded, buddy. That's my oh no. Website owners create MCP servers inside the websites. And so either injected by browser extension or created. Broadcast MCP. Time server transport. Server transport. Here there is an extension of the model which allows you to treat your website as an MCP server which can be discovered. Yep. Well, okay. The actual idea is not. It's fundamentally useful because, and I think I've brought this up in several videos in the past, where I find it so ridiculous and dumb that we're building or we're optimizing tools that are supposed to help agents to navigate the web via the browser as if it was a user, where it's like it types a website address, it looks at the page, decide which button to pick, which form field to choose, and then enter a message. I find it incredibly dumb because there's no reason why an AI agent needs, like, at least conceptually. I know your market forces, and if it can be done, it will be done. And if people will pay for it, people will build it. But conceptually, that just feels really dumb. Like it forces a very human-centric view of accessing data on the agents. Like it's so inefficient for an agent to have to crawl a bunch of HTML nodes, decide which one to pick, and all that, when really all it really wants is read data and write data. So I mean, yeah, this could be interesting. Honestly, yeah, I'll give him a follow. Do 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 do. Okay. Let's see. Anna's archive. What's Anna's archive? Oh. I feel like I've never heard of this before. I'll save this. Never know. Jank programming language. Flipper Zero clone. What is Flipper Zero? Oh, okay. Embedded stuff. Tree borrows. What are we talking about here? Reject all cookies. This is a research paper. There is some code. Well, it's not on GitHub. And what is V? Is that Varus? Varus? Let me see. Sounds like Varus. Is it Varus? Varus? Don't distinguished paper appeal the eye. Ooh, that's some big brain stuff right there. Are the papers out? The list of papers. Alright, we're putting up the second port, we consider application on this carries out automatic sacrifice sound call. Sounds interesting. Wait, how do I all details? Where's the actual paper? Yeah. Also, is it already on YouTube? Oh yeah, it's already on YouTube. Yay.
So, hello everyone. So, first of all, I would like to thank Luca and Guillaume for the invitation. So, today I'm going to talk about a static analyzer called MemCAD, which was designed with a bunch of people, many of them to cite in a single slide, so I will cite them when I come across specific topics. So what are we going to try to do here? Well, first we are doing static analysis, which in general is a way to compute semantic properties for programs using some kind of conservative approximation. So we are going to use abstract interpretation. And it has a very wide range of applications, some of which are not so common.
Okay. I have to reserve this for later. Oh. Guess I'm not subscribed on this particular YouTube account. Let's see, what's the playlist? Oh no, I've added a bunch of stuff recently. I do tend to check this channel often, and I saw my other YouTube account. Oh, actually, let's look at playlists. SPLDI. Kenji language. Lots of juicy stuff here. Oof. That sounds interesting. Efficient linear usability monitoring. Oh, that sounds interesting too. What do you guys think? Should we try one of these? Yeah, let's try this. Only because I've been looking at Porcupine. I'm thinking about doing a port of this in Rust. It's a linear usability checker.
He's going to present his work. Let's give him a big clap.
Okay, so thanks for the introduction. So this is joint work with me and my supervisors, Paros and Bengt, and the two people from IIT Bombay, Krishna and Om. So I'm just going to move my mouse cursor because that's going to irritate me. Okay. So you have a concurrent system, and oftentimes they communicate through some shared object. And this shared object is, for instance, a stack or a queue or something like that. And this, to reason the correctness of such a system, we need a correctness condition that's hopefully composable and that captures this interacting with a common object. And once the standard such correctness condition is linearizability. And linearizability is a way to extend a sequential specification, like the ones for stacks or queues, for instance, to a specification in the concurrent setting. And it does so by taking an execution. So this is an execution. We have operations that are these pushes and pops, and we have they're called.
Sorry. Da, 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 da. No. Oh, that's not GitHub. I mean, it's fine, but in the thing, I think they said GitHub, right? It's openly available on GitHub, but there's no link to it. Limo. Let's see if Google can help me find it. No, that's not what we need. Oh, these are the slides. Nice. Now, can I wait, what? That's dumb. Okay, I think this is it. This is the one. Yeah, 3 months ago. Okay. Hey, I'm the first one to fork it. Look at that. Yeah, I mean, I do wonder how it compares to Porcupine.
False is the left point of these lines, and the returns are the right points. So linearizability says, well, this history is considered linearizable if we can pick a time point in each of these operations, or alternatively extend the partial order that happens before order into a total order, such that this now sequential history corresponds to the definition of, or to the specification of the original sequential structure. So this is a stack execution, so the original history was linearizable. And we are specifically looking at the monitoring problem, which is when we take an execution like this and ask, is this linearizable? We're not looking at implementations. So we just expect a sequence of calls and returns to be so.
We're looking at if is a given execution concern. By the way, I think you can also probably run this on the Limbo simulator, although no, I guess not. You can augment the Limbo simulator with this, although I would expect that part of the way it's implemented already, maybe implicitly, checks for linearizability. But yeah.
Operations. And unfortunately, this is NP-complete in the most general case, even for simple structures such as registers. So we have to make some additional assumptions. And a common such assumption is that the histories are differentiated. And this means that each value just occurs in, at most, one adding operation, so a push, and removing operations, a pop. And in fact, this is a very sound assumption, because it turns out that for implementations, if you have an implementation that implements a stack, it is correct, like it's linearizable, all its executions are linearizable, if and only if all of its differentiated executions are linearizable. So it suffices to just look at this. So, and the second, or rather this is a non-differentiated history. And the reason that we can do this is that this history, this non-differentiated history, is linearizable if and only if there is some differentiated history that we can obtain by just renaming it, or rather we can obtain the original history by renaming the values of this differentiated history. Okay, but this is a tricky problem apparently, because this is linearizable, we just saw that in the first slide, but this is not. We only swap the order of two events. So it's not always easy to see whether it's linearizable or not. And in fact, this as shown in previous work. So we have, in our paper, we have found errors in previous work, notably this is a quite recent paper on this that produced a quadratic time algorithm for monitoring stacks, which is incorrect. It does not differentiate between the two histories on the previous slides. And there was an attempt earlier in 2018 for an algorithm for something that is more general, for a class of structures, which also was incorrect, because you found a bug in the proof. The algorithm, we don't know, but the proof for it was not correct. So, we'll present our algorithms that we have proven are correct. And for stacks, it's quadratic in the length of the history. And we do this by computing what we refer to as populated and distorted segments of this.
Somebody proves
the stack history.
it's actually not correct 2 years from now.
Values, or we partition it. I'll get to this. And if we ever cannot progress, we conclude that it's not linearizable. Okay. So the first thing is that we can ignore the threads. So here we have 3 threads that are performing operations, but the specification itself says nothing about the threads. It just cares about when things call and return. So we're just going to draw it slightly differently and just put the values side by side. Okay. So the first thing we do is we compute what we refer to as the cover. So between the return of the push for any value and the call of the pop for that value, we know that that value must be in the stack. Okay? So what does that mean for when we take the union of these? Well, that means that in this yellow, what we call the populated segment, which is the union of these covers, there must be at least one value in the stack. Okay? And in these green regions on the sides, we know that the stack may be empty, because everything that's already been pushed has also had its pop called. Okay? So what do we do? Well, we start by finding extremes. So we see here that the push to B intersects the leftmost deserted segment, and the pop to B intersects the rightmost deserted segment. So we can just put B at the ends. Push B first and pop B last, okay? And then we start again.
Wait,
We
what?
do the cover, the deserted segment, and the pop to B intersects the rightmost deserted segment. So we can just put B at the ends. Push B first and pop B last, okay? And then we start again. We compute the cover, we compute the populated and deserted segments, and this time there's no extreme value. So what we do instead is that we see here that in this middle, we have an inner deserted segment. And this means that there's some values whose pushes happen before this, the populated segment to the left of it, and whose pops are called at least here, at the start of this deserted segment. And similarly, there's a populated segment here, so that we know there must be something to the right. So what we do is we just separate the history here. We say that, okay, well, we do whatever we want to do with the left side, which is A, and then we do whatever we want to do with the right side, which is C and D. Okay. So we look at the left first. Well, we do the same thing. This is maybe a bit easier example, but because we can just, it's extreme, we put it like this. And then we move on to the right side, we find the cover, we find the populated and deserted segments, we find that they are extreme, and we put them like this. We have found linearization.
Wait, so if I understand right,
it's extreme. We put the cover, we find the populated and deserted segments, we find that they are.
the cover means the area where you have all segments in it at the same time. Okay.
Are extreme, and we put them like this. We have found linearization for a second example, but because we can just, it's extreme, we put it like this. And then we move on to the right side, we find the cover, we find the populated and deserted segments, we find that they are extreme, and we put them like this. We have found linearization, hooray, the history was linearizable. Great. Well, we made some additional assumption. The first is that we assume that every history is completed, like every push has a matching pop. But if there are some pushes that do not have matching pops, we can just add concurrent pops at the end for those values, because we know that they will be in the stack at the end, because they're not removed. And the second thing is that pop operations might return, nothing, indicating that the stack is empty. And in such a case, we can just start like this. We can compute these again. And all of these that intersect a deserted segment, we can just remove them, because we know that the stack can be empty there, so remove it. Well, we still have one left, so this is not linearizable. Okay. Well, and the complexity, just to go through it, it's we sort the values, we compute the deserted and the populated segments in linear time, we find the extreme. In linear time, we partition in linear time, and then in the worst case, each of these steps that we perform just removes one value. So n steps, computation, n squared. So, Qs. Here we do a bit better, we do M again. And we do this by exploiting a small model property, which is that a differentiated and completed Q history is linearizable if and only if, for no values A and B, we have that A is incubed before B and B is decubed before A. So we can just look at what we call critical pairs. So, yeah. And it's important to note that this is not all for stacks. We can not use any property like this for stacks. In fact, in our paper, we show that we have a construction for a counterexample to there being a small modular property of size n for any natural number n. Okay, so what do we do? Or rather, this we look at this small modular property expression here, and we compare this to these lines. So what does it mean? Well, it means just that the entirety of the operations could be, from its push call to its, or enqueue call to its dequeue return, is contained within the inner or the cover interval for some other value a. Okay, so we just need to check containment for these intervals, and that we can do by constructing a tree. So we're going to construct what we refer to as a Q tree, and then scan it for the containment. So the Q tree is a red-black tree that contains a left and right subtree. It contains left and right endpoints for the inner interval, so it contains the inner interval for every value. And then it contains a high key just to help, which is the highest right endpoint occurring in subtrees, just to help us do the search without branching. Okay, so here's a big history. These are its inner segments. So here we have, for the value 0, we have its enqueue returns at 3, its dequeue starts at 6, so we have the inner segment 3 to 6. Okay, and the outer segments, for 0, the enqueue starts at 1, the dequeue ends at 8, so the outer is 1 to 8. Okay, so we're just going to go through one of these containment checks. So we're going to ask if this outer segment, 1523, is contained in something else. So we start at the top. Well, 15 is less than 16, so we should probably go left. Okay, here we see that, okay, it's not contained in this interval. 15 to 23 is not contained in 9 to 14. Okay, so we look to the left first and see that the high key in the left subtree is not big enough to contain wherever we go here. This high key is going to be too small. So we just proceed to the right instead and find this interval, and we have containment, so the history was not linearizable. And again, go through the complexity. Constructing the tree is n log n. Each search is log n, and we do n searches, so it's n log n. Okay, and finally, the simplest of the three is a multi-set algorithm. This is in linear time, and we do this by simply first stating that a multi-set history, or set history, is linearizable if every single valued projection is linearizable. So if we can just look at one value at a time, and essentially arrive counters. And then one of these single valued histories is linearizable if and only if the number of returned removes never exceeds the number of called adds. So we can just count, and we're done. Okay. And then there are some other operations you might want to be able to do on sets, for instance, containment checks, main membership queries, and we present in the paper, we have a greedy algorithm for handling those. So, in conclusion, we have some monitoring algorithms for stacks, queues, and sets. And we have found issues in previous work, and yeah, we have shown that these are correct. So, for future work, I want to formalize this in a theory improver. It's sort of work in progress on the side, just to be absolutely sure there's no mistake anywhere. And then to extend this to other structures, such as snapshots or other concurrent objects. And then finally extend it to related correctness conditions. For instance, durable linearizability. There's also k-linearizability and other similar properties. Okay, and thanks for listening. And I am finishing up my PhD, and I'm looking for work. Hello, come talk to me.
Any questions?
So can you go back to the multisets?
Yeah, sure. Can try. Yeah.
So over here, the number of return remove never exceeds the number of called add. Even if this condition is true, it may so happen that you have more removes before the adds.
Yes, so this was for, wait, no, you cannot have more removes than adds even if you have this.
So when you say multiset, it means the same value can be entered many times?
Yes, but if you remove, you remove one
and
of
it
them.
is, oh, sorry?
Yes, if you remove one of them.
And then can I remove again if I had
Yes,
two?
so if you add, remove is valid.
Yeah.
So, okay, what if the history is such that the first three are removed and then I see an add and they're all ordered like this, remove, 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 add, add, add. The numbers will be the same, but then it will
No, but you look at each, maybe this could have been more clear. So you look at each time point, the number that of returned removes and the complete and called adds.
Okay, so for each
before
prefix.
Yes, prefix.
And how do you talk about a prefix in a history? It's a partial order, so.
Yeah, I mean, we can just well, the events are in total order. So each push, each call and return, these events form a total order.
Okay.
So we can just go through the events and count.
So when do I count a remove operation to be there? At the call time or at the return time?
Return time.
I see. Okay. And can you go back to the queue?
Sure.
So over here,
Where?
Yeah. So next slide.
Next slide.
So over here, the time complexity is n log n, and it is not just coming from the initial sorting of the.
No,
It's
I mean,
also-
constructing the tree is n log n, and that's just one thing, and then it's plus this, where we do n searches, each is log n.
Okay, thank you. And one last question.
Yes.
So, the stacks and queues, and even for multisets, I think, would you be able to carry out this exercise if you had peak operations?
So I do not know if these algorithms are very compatible with peak operations, because so right now so peak operations basically can act sort of like a similar as a pop operation in that it constrains it in the same way that this actually has to be here now, but we would need to do some additional reasoning for that, and I don't know how to do that, at least not by extending these algorithms.
Thank you.
One more question.
Hi, so this is a bit of a tricky question, but since you did mention, so you mentioned that you have found some faults in the proofs of previous works.
Mhm.
How confident are you in your current proof?
I know.
I'm fairly confident. Written.
That's what I said a few minutes ago. I was like, oh, okay. He was very confident saying, how everybody else's proof was wrong. And so I was like, oh, okay. So you think yours is, basically thinking you're that guy, What happens when a year or 2 years from now, somebody says the same thing about your proof, huh? Anyway, I'm glad somebody else in the audience was thinking the same.
And then done them again, and then had 2 or 3 people double check them. So I'm fairly certain.
Can you mention what's the actual bug you found in the previous proofs?
Okay,
Yeah.
so the bug in a proof we found was, let's see if I remember the correct terminology. They presented a hornification procedure for what they called operation order specifications, and it turns out that this hornification procedure was not sound, and their proof for its soundness was incorrect.
Thank you.
One very short additional question.
Thank you. Eris Petrang from Technion. So when you say monitoring, do you mean that you go step by step, and when it's not linearizable, you shout, "This is not
Yes.
linearizable"? Okay. So did you try to look at the not strong linearizable things, where you simply don't know at the point?
So that's part of the future work, right? Related
Snapshots.
conditions. No, snapshots is one line of work, right? Other structures, but then also other correctness conditions. So non-strong, weaker forms of linearizability.
Yeah, it's still linearizability. It just doesn't have an extra strong property. Maybe. I mean, there's a paper on strong linearizability,
Okay.
and there is a difference if you, at the end of the execution, you look for an order, or you know at any point if things have been linearized or not.
Okay, yeah, okay,
So-
okay, yeah, okay.
And some snapshots are not like that.
No,
You cannot.
I'm not sure that even stacks are either.
No, these are
So-
strongly whatever
Okay.
you gave is strongly linearizable.
Sorry, we probably
No problem.
should wrap up here because time is a little bit over. So let's thank the speaker again.
Hello, good afternoon, everyone. My name is Min Jian. I'm from the University of Illinois at
And Samuel,
We have another treat especial. Shenyu's here to tell us about the Qiangqi language out of Huawei, part of the Harmony OS. I often hear people complain that we don't get enough papers and talks about language design. So if you've ever felt that, you are in for a treat. We've got one here. Please take it away.
Thank you. So this is Xinyu Feng from Huawei Programming Language Lab, also from Nanjing University. So I'll introduce the Changjie language at Huawei. Changjie is a new programming language for mobile application development on Harmony OS, which is a new operating system for Huawei mobile devices. So with this new language, we can have better vertical integration of the whole hardware and software stack to deliver a better programming experience or performance to our developers. Also, the language itself is a general purpose language. It can be applied in other scenarios like microservices. So the language is a modern statically typed and garbage collected language with ARVM-based backend. It supports native compilation. it's also a multi-paradigm language. So the name comes from the ancient Chinese sage who is supposed to be the inventor of Chinese characters. So here we have a nice picture of this person. Whereas the other languages, this is not intended to be a thorough comparison or fair comparison, just to give you some idea how these features are adopted in other industry level languages. This is a lightweight thread in Changjie. We use this spawn keyword followed by a language.
And I guess that's the goal. These are more like, so these follow more of the Go async model rather than no Rust async model, right? Usually when I'm trying to remember the stack versus stack full versus stackless, that's what I go with. And Go is stack full and Rust is stackless.
Instruction to create a user level
If I
graph
remember
returns
right.
a future type so that you can get the return value of this lambda. So the implementation is stack based instead of stack based, so that at the programming level we don't have to worry about this async await the modifiers. It also supports dynamic stack expansion. So we have a low latency concurrent compact GC. This is quite important for UI intensive applications where people really don't want to have delays during the operation. So in the implementation we introduce read barriers for global variables so that we can eliminate some of the synchronization points and reduce the delay of the stop the verb period. And on the right-hand side, we have an experiment showing that the delay time for Changjie is the blue numbers, which is usually below like 10 milliseconds. Most of the time, it's around 1 millisecond, which is quite reasonable. Also, I want to point out that the implementation is based on ARVM. It's a moving GC, so it could potentially be a test cases actually, because with some experiments, actually, we can now support this different style of domain-specific language.
They have it embedded. They see embedded DSLs. Wait, so that support Prolog. What else? HTML. SQL. Oh, post condition.
It's embedded in Changjie, like HTML or SQL or Prolog like style programs. Also, we have a preliminary
That's
implementation of
interesting.
context programming so that people can use annotations of pre and post condition environments and then do this some runtime testing. As an example of our domain-specific language, we also have an implementation of agent DSL. We call it Changjie Magic, which is now an open source project online. So in the language, we can have a simple configuration of an agent about the models and the planning strategy. We also have several prompt patterns provided to simplify writing prompts. Also, it has a syntax for multi-round conversations with agents, and the framework also automatically maintains the chat history. We also, with operator overloading, we introduce have a declarative style of multi-agent coordination. So next, I will spend some time to introduce the support of effect handlers in Changjie and some of the applications. So many of us are already very familiar with effect handlers. So here in this try block, when we perform an effect, it's like a throwing exception. So we jump to the handler, and then we get this resumption as a first class value, so that it can be stored in variables. It's like a continuation. Then later on, we can use this resume to jump back to the place where we perform the effects. So we know this is a very powerful language feature which can be used to implement all kinds of control abstractions like code routines. But at the same time, it could be overly expressive. People may abuse this to write unreadable code. So that's why we also introduce a more limited form we call immediate handlers or resumable exceptions. Here, resumptions are implicit. The programmer don't have access to the resumption value. In the handler, they can only either block the resumptions or do the resume immediately. So the resumption cannot escape the handler block. So even with this limited form, we found it's already very useful because this kind of dynamic scope of handlers, it gives us the ability to implement something like dependency injection. And also it allows more efficient implementation than the general form. So next I'll introduce some of the experiments we do based on these immediate handlers. So in our UI programming, on the left-hand side, we write code to configure the parameters of the UI components. Actually, for each line of the code, the underlying implementation calls the native C++ code. So as you can see from during the execution, so we always go across the boundary between Changjie and C++, go back and forth. This introduces lots of performance overhead. To address this problem, the so-called FFI coalescing tries to intercept all these foreign function calls from the Changjie side and batch them and forward them to the C++ side. So in this way, you only go across the language boundary once. Okay. And then we use this effect handler to collect all these function calls. So the idea is that in our original implementation, we do the foreign function calls directly, but now they are just effects. Then in our handler, we collect all these function references and arguments and put them in this list. And then after all the function calls are collected, we forward them to the C++ side. So the next application is to use effect handlers to do some kind of reactive state programming in the UI framework. So UI stage change to collect all these function references and arguments.
I don't know why, but the more I'm looking at it, like just the syntax alone, but also explaining the way, hearing the explanation, I don't know, it just kind of works. Like, I like it. I don't know, maybe it's just the newness of it, but this feels like it's more tasteful than the single weight syntax. I feel like this makes it explicit that you have the effects boundary is more explicit. At least that's the impression that you get. I don't know, I like it. I think I like it.
In our handler, we collect all these function references and arguments and put them in this list. And then after all the function calls are collected, we forward them to the C++ side. So the next application is to use effect handlers to do some kind of reactive state programming in the UI framework. So UI state changes require querying the UI tree to identify and update these dependent properties. So then to do this, we define these state operations as effects. And then so in this try block, we may access the states. And in the handlers, what we do is actually checking the dependency relation. And also we propagate these state updates along these dependency relations to implement this reactive programming. And the next application is a domain-specific language, which is similar to CSS-style programming for component configuration. So here in the UI code, we can see that for the same kind of components, we usually have the same style configuration here. So it's a lot of redundant code. Actually, we try to define this kind of configuration as effects. So we do this configuration in the effect handler. This way, we can have this nested style definition, which is very similar to the familiar CSS programming. So these are the main language features. Next, I want to introduce some of the key challenges and the ongoing work. So the first one is about DSL programming. As I explained, that we want to use Tangi as the host language so that we may have embedded DSL, which means we want to support mixed programming of the host language and the DSL language. So in this example here, in this DSL program, it may refer to variables and types defined outside in the general purpose language. So the challenge here is to provide a unified language experience between its host language and DSLs. So another issue, which is also well known for people working on meta programming. So the problem is that we want to lift these error messages generated by the compiler for this general purpose host language to the specific domains. So in this example, it's a very simple example. The code on the top is trying to do some addition of vectors. So A and B are supposed to be arrays. But here there's a mistake. So B is an integer. So the expected error message should be the complaint about type mismatch. But if we expand the code, expand the macro, actually we can see that the code below accesses the size field of B, also to use the indexing operator to access the elements. So we'll get complaints like there's no size field for integer type, or there's no indexing operator for integers, which would look totally confusing to these domain programmers. So the next problem is about cross-language interoperability. I think our previous work explained this issue very nicely. So the interaction between this managed language and C++ causes lots of memory safety issues. Actually, in Tangi, this is also one of the major sources of memory safety problems, although Tangi is supposed to be a memory safe language. So to address this problem, we probably need some tools to support cross-language program analysis. Also, we need to introduce rich types, as also mentioned in our previous talk, to have a nice signature for these foreign functions. But here's another issue, which is the interaction between managed languages, which probably not so thoroughly studied. So here, Tangi need to call libraries of other languages like Java or FTS. FTS is an extension of TypeScript, which is also an application language for Harmony OS. So here, in this kind of a scenario, so both languages have their own graphic characters, and the graphic characters need to cooperate. Then there's this nice PRGI paper actually found out that we have several issues. Actually, these issues also show up in our in the real programs and our projects. So one of the problems is that the nodes, the objects may follow cycles on both sides of the problem is it still doesn't have a good support. The third issue is for API stability. So high-level languages permit that we have better abstraction. People usually don't need to worry about this low-level implementation detail. Application need to do this dynamic linking. Careful with the trade-off between flexibility versus performance. One way is that we hardwire all these API formats. API performance. So these are some of the completion time with some incremental or parallel completion approach. So there are also other problems which are on the list. So anyways, we have on the website, we have an online playground people can try if you are interested. So feel free to try and contribute. This is the end of my talk. Thank you. The so-called vertical integration. So
hi, this is Someone from NYU. I'm really curious about Tangi being built with Harmony OS in mind. Are there any different technical considerations such as scheduling, because you're working now in a microkernel architecture rather than a monolithic kernel?
Yeah, actually, indeed, scheduling is actually one of the most feature that we want to have a vertical integration, so-called vertical integration. So one of the issues that we have is that applications may want to create too many threads, they may be selfish, and so then the uniform system level scheduling, thread management mechanism can have effective control of this. So the language wants to have a good coordination between with the system level scheduling approach.
Hi, Thomas Gilroy at Washington State. Really enjoyed your talk. You mentioned that you're able to optimize these second-class resumptions for effect handlers. I'm wondering if that makes the stack kind of like a zipper structure, or if you're using inlining, if you can speak to what you're able to do to optimize these, given you don't have first-class control.
Well, I'm not an expert here, but I guess what I heard was that because this resumption doesn't.
Okay. Welcome, everyone, to the industry session. We are very fortunate to have several fantastic talks. To kick things off, we're going to figure out what to do about the problem of memory unsafe languages. So I feel like at PLI we already know the answers. You can never speak the language, duh. But the reality is there's billions of lines of code that aren't going away. And so to figure out how to gracefully make this transition and have things work together, and it's an incredibly hard challenge. So Yoel's going to tell us about work going on at Apple to make that happen. Let's welcome our speaker.
Anyway, as you may have already noticed, yeah, it's a great channel to look at. It's pretty diverse in the kind of content, programming / computer science content that's available. So give it a try. Anyway, I think I'm gonna call it for tonight. We'll be back tomorrow for part 4 of the gosh, what is it called? Coordinated progress, the blog and the series of posts from Jack Vanlightly, and thank you for watching, and if this was useful in any way, just please like and subscribe, and I'll see you around.